Today we will take up lecture 12. You may recall that in lecture 11 we had introduced the second moments of area and products of area. Also we learnt about the parallel axis theorem, which enabled us to find out the second moments and products of area about axes which are parallel to a set of given axes passing through the centroid of the body. So, under a translation of axes we could determine the second moment of area and product of area when these quantities are given in some original axis. Okay. So, we will continue with the topic on properties of surfaces. Today we will look at the transformation of second moments and product of area when the axes are given rotation. For example, in this picture we can see that the axes x, y, z are given and a new set of axes is also given, which is x dash, y dash and z dash. The new set is obtained from the old set of axes by rotation through an angle alpha as shown here about z axis. So, that is why z and z dash axis they are coinciding. So, when such a rotation is given, what is the effect on the second moments of area and product of area? Can we correlate the new quantities vis-a-vis the old quantities? The answer to this question is yes. In order to obtain such a correlation, let's look at the new coordinates x dash and y dash. Going back to the picture, the figure, we will see that let us say, suppose I consider an arbitrary small element of the area, namely the element is having dimension dx and dy. Now, this element is having coordinates x and y in this plane, and in the new coordinates system the coordinate of the same element are x dash, y dash. We can correlate x and y with x dash, y dash by simple trigonometry. For example, if I consider x dash, I can project it on old x axis and old y axis. Similarly, if I take y dash, I can again project it in x axis and y axis, and we can see that the following relation will be obtained, that is x dash is equal to the new x coordinate, that is to say is equal to x, which is the old x coordinate, times cosine of the angle of rotation alpha plus y times sine alpha. Similarly, the new y coordinate, that is y dash, is equal to minus of x, that is old x coordinate, sine alpha plus y cosine alpha. Okay. Now, by definition of the new second moment of area about about y axis, that is I x dash is equal to, by definition, area integral of y dash square when this integral is taken over the entire given area. And substituting for y dash from the previous equation, we will have it minus x sine alpha plus y cosine alpha whole square area integral. This integrand is expanded, and since alpha is constant, therefore sine alpha and cosine alpha are also constant. So, they can be taken outside the integral. So, sine square alpha times area integral of x square dA plus cosine square alpha area integral of into area integral of y square dA minus 2 sin alpha cosine alpha into area integral of the product term, that is xy dA. Well, these integrals yield the well known quantities, that is x square dA area integral will give me Iyy, that is in the old coordinate system. So, Iyy sin square alpha, that is the first term. Similarly, y square area integral will give me Ixx, therefore, Ix plus Ixx cosine square alpha minus 2 times the last term gives me the product of area in the old coordinate system, 2I minus 2 Ixy sin alpha cosine alpha. So, we have basically set up a relationship between Ixx, Ix dash, x dash and all the 3 quantities in the old reference system, that is Ixx, Iyy and Ixy. Well, this relationship can be also recast in a slightly different manner by using trigonometric relations. So, because sin square alpha and cosine square alpha, they can be expressed in terms of cosine 2 alpha through trigonometric identities, and after simplification it is very easy to come to this final result, that is Ix dash x dash is equal to Ixx plus Iyy divided by 2 plus Ixx minus Iyy divided by 2 into cosine 2 alpha, okay, minus Ixy. Well, this 2 times sin alpha cosine alpha will be easily given in terms of sin 2 alpha. So, I have the second moment of area about y axis, that is in the new coordinate system, that is Ix dash x dash is equal to the corresponding terms in the old coordinate system and cosine alpha, cosine 2 alpha and sin 2 alpha terms. I could do the same analysis, same procedure for I y dash, that is the second moment of area about x dash axis, that is in the new coordinate system. Either I go through the same expressions, take the squares and simplify, and or there is an alternate quicker method, that is if I replace alpha by alpha plus 90 degrees, you can see from the figure that this y dash will make an angle of alpha plus 90 degrees with x axis, old x axis. So, if I substitute alpha by alpha plus pi by 2, then the relationship is very quickly obtained. I y dash is equal to Ixx plus Iyy by 2 minus, because of cosine terms. So, that will lead to cosine 2 alpha plus pi. So, it will give me minus Ixx minus Iyy by 2 into cosine 2 alpha plus sin 2 alpha, Ixy sin 2 alpha. Okay. Well, let us do the relationship for the product of area, that is Ixy terms. So, Ix dash y dash, that is product of area in the new coordinate system, is to be related with the corresponding quantities in the old coordinate system. So, by definition this is equal to area integral of the product term X dash y dash, and again substituting for x dash and y dash from the relationship which we have obtained earlier. So, you get this term for x dash, this second term for y dash, and then you take the area integral over the entire area of given area, and this product term is now simplified, and again going through the area integrals we can come to this result, that is I x dash y dash, the product term in the new coordinate system is equal to sin alpha times cosine alpha into Ixx minus Iyy. These are the two second moments in the old coordinate system, plus cosine square alpha minus sin square alpha into the product of area in the old coordinate system, that is Ixy. Again these square terms can be replaced by through trigonometric identities by the sin 2 alpha and cosine 2 alpha terms. So, we will have Ix dash y dash is equal to Ixx minus Iy by 2 sin 2 alpha plus Ixy cosine 2 alpha. So, what we have achieved is that the moment of area and product of moments of both the moments of area and product of area in the new coordinate system can be correlated with the three quantities in the old coordinate system, which we have already calculated, for example. So, with the help of these relations we can calculate very quickly those quantities in the new coordinate system. These coordinate systems are related through rotation about an axis normal to the area, that is z axis. Now, looking at the relationship for Ix dash x dash and y dash y dash, if I add up these two equations which we have already obtained, then you can easily see that these two last terms will cancel each other, and again you can see that we will be left with, because there is a negative sign here, positive sign here, these will also cancel each other. So, we will be left with Ixx plus Iyy. So, the sum of the second moments of area about x axis and y axis in the old coordinate system is equal to again the sum of second moments of area about the new coordinates, that is x dash and y dash. So, this quantity is independent of alpha. So, what does it mean? It means that for any alpha the sum is constant, it is invariant. That is a very useful result and it is a very basic property. Now, I think we can all grasp these concepts better by taking up an example. The example is find Ixx and Iyy and Ixy for the rectangle. Okay. This rectangular plate is given, we have been asked to find Ixx, Iyy and Ixy. Also compute the polar moments of area about axes passing through point A and B. If you recall, we had in our last lecture introduced at the concept of polar moment of an area, given area. Okay. So, first of all, what we do is, suppose I have these quantities and these axes x dash axis and y dash axis, and the new axis is xy axis, which is obtained by rotation through, let us say, if I call this as an angle alpha. So, tangent alpha will be equal to 1.2 divided by 3. This is 1.2 and this is 3. So, 0.4. So, alpha will come out to be 21.8 degrees, and since we need cosine 2 alpha and sin 2 alpha in this in the relation, 2 alpha will be equal to 43.6 degrees. Okay. Now, first we will find out Ix dash, Ix dash x dash, y dash y dash and Ix dash y dash, that is about this base and about this side. Okay. Well, if I have an axis passing through the centroid of the area, that is through the center of this diagonal. So, this you can say the half the width and half the base. So, this is the centroid of this rectangle. We will first find out the second moments of area about these dotted axes, and then by parallel axis theorem we can shift these to x dash axis and y dash axis. So, the procedure is once again like this. First of all, this rectangle is given. Okay. So, forget about x y coordinates for the time being. I am considering only x dash y dash coordinates. Now, to calculate the second moments and product of area about x dash and y dash coordinates, since the second moment of area about the axis passing through the centroid, that can be obtained from handbooks or it can be very easily calculated. So, namely it is BDH cubed by BD cubed by 12, that is B is the width, D is the depth cubed divided by 12. So, if we consider that formula, we can calculate, let us say first of all this axis, second moment of area is easily obtained about this axis, then this has to be translated, this has to be transferred to x dash axis by parallel axis theorem. Similarly, I will calculate the second moment of area about the vertical axis passing through the centroid of the rectangle and then shifted through parallel axis theorem. So, that is the procedure. So, first I will calculate I x dash x dash. Now, width times depth cubed by 12, that is about the middle axis, and then by parallel axis theorem, parallel axis theorem means area times the distance between the two axes squared. So, area of the rectangle is 3 into 1.2 times the distance. Distance is this distance. So, 1.2 by 2, that is 0.6. So, into 0.6 square. So, that will give me 1.728 meter 4. Similarly, y dash y dash, that is the second moment of area about the side. So, again we will have BD cubed by 12. Now, B is the width 1.2 times D depth is 3 cubed by 12 plus by parallel axis theorem area times the distance square. Now, the distance will be 3 divided by 2, 1.5. So, area times 1.5 square. So, this is exactly what we have done. I y dash is 1 by 12 into 1.2 into 3 cubed plus area is 3 into 1.2 times the distance square 1.5 square. So, this comes out to be 10.8. Now, for the product of area, now the axis passing through the centroid of the rectangle, they are symmetry axis. Rectangle is after all a symmetric body or figure about the central axis. So, we have already seen that if the axes are passing through the centroid, then the product of area terms are 0. So, xy about these axes will be 0. So, then if I want to shift them to x dash and y dash, then again parallel axis theorem for the product of area, which means that the area times the distance between the x axis and into the distance between the y axis, E into D into A. So, look here, I x dash y dash is equal to 0 plus 3 into 1.2, that is the area of the rectangle, into half the side into half the base, 0.6 into 1.5. So, that comes out to be 3.24 meter 4. So, it means I have obtained I x dash, I y dash, and I x dash, y dash about the side axis, about the sides of the rectangle. Okay. And then I have to shift these quantities about the inclined axis. Oh, sorry. These inclined axis at angle alpha, which is 43.6 degrees. So, x axis and y axis. So, I have to use the rotation formula. So, if I rotate it now through 43.6 degrees, then I will get Ixx by use of the formulas, cosine 2 alpha again we have got, and we will get it 0.7452 meter 4, and then we go to Iyy 11.7828 meter 4, and then the product of area, that is 0.78 with a negative sign, 0.7818 meter 4. You may recall that Ixx and Iyy are always positive. So, indeed we are getting positive results for Ixx and Iyy in any coordinate system. But Ixy, the product of area term can be positive, negative, or even 0. Here we are getting it negative. So, it is all consistent with our general conclusions. So, Ixy is obtained by the same transformation formula as minus 0.7818 meter 4. Now, we want to find out the product of the polar moment of area. The polar moment of area, recalling from last lecture, is sum of the two second moments of areas, that is Ixx plus Iyy. So, I polar at an angle of at a point A, at the corner A, this corner A, and the second is corner B. So, will be equal to the sum of the two Ixx and Iyy. So, 0.7452, that is Ixx, and this is Iyy, which comes out to 12.528. Okay? And this is the invariant quantity. And for point B, since it lies symmetrically about the centroid, you can easily see that whatever happens to this, same is over here. So, if our z axis is over here and z axis over here, then by parallel axis theorem we can see that although on one side the distance is positive, on the other side distance is negative, but when you take the square it will not make any difference. So, it means that polar moment of area about point A is equal to polar moment of area about point B. So, I polar about point B is equal to I polar about A. Okay. That is why we will have this result, and the value will be equal to 12.528 meter 4. So, that is all I have to say about the moments of area and products of area. Now, we will continue our lecture, but in a slightly different topic, on a slightly different topic, and that is the moments and products of inertia of a body. Now, we are no longer dealing with only areas, which is a two-dimensional concept. Now, we will be dealing with body, which is a three-dimensional continuum, and we will also show that when the body is a plate-like body, that is a thin body with uniform thickness, then there is a direct correlation between the second moment of area and the product of area with some quantities which we will very soon be introducing, that is the moments of inertia and the products of inertia of a three-dimensional body. So, let us start with it. Moments and products, these terms refer to the distribution of mass of bodies in reference to given coordinate system. That is, if you are given a body and a coordinate system, whether the mass is closer to the origin or farther away from the origin, how it is distributed around the origin, etc., etc. So, that concepts will be manifest through the moments and products of inertia. So, let us define what are these quantities. So, if I refer to the figure here, let us say this is a three-dimensional body and an arbitrary coordinate system x, y, z, and I consider a small cuboid of the body or element of the body whose mass is dm. Okay. So, this element is located at a position vector r, which means that its coordinates are x, y, z. X coordinate x is parallel to x axis, coordinate y parallel to y axis, and coordinate z is not shown, which I am showing now. This is parallel to z axis. So, if I now consider that element whose position vector is vector r is equal to x times the unit vector I, y plus y times unit vector j plus z times unit vector k. Then by definition the mass moments of inertia are the volume integral over the quantity, volume integral of the quantity y square plus z square, the y coordinate square plus z coordinate square times the mass density. Rho is the mass density of the material in kilograms per meter cubed. So, rho times dV is nothing but dm, the elementary mass, times the y square plus z square. This is simply the distance from the x axis by Pythagoras theorem. Similarly, Iyy is dm times the distance from the y axis square, volume integrated over the entire volume of the body, and similarly Izz is equal to volume integral of x square plus y square rho dV. So, mind you, the quantity rho can be variable quantity. It need not be uniform, that is, rho can itself be a function of x, y, z if the body is non-homogeneous. Let us say body consists of a mixture of several types of materials, copper and steel, or soil and water, or something like that. So, from point to point the density of the particles can be variable, then rho is itself a function of x, y, z. But on the other hand, if the body is homogeneous, then rho is a constant quantity and it can be taken outside the integration sign. Second set of three quantities are the product of inertia quantities Ixy, Iyz, Izx. Now, definition here is much simpler. It is the volume integral of rho times xy, that will give you Ixy. Again, volume integral of rho times yz will give you Iyz. Rho times zx, volume integrated, I will get Izx. From the definition, it is very easy to see that Ixy is equal to Iyx, Iyz is equal to Izx, Zy, etc. Zx is Izx is equal to Ixz. So, the product of inertia terms are symmetric, okay, because the order of multiplication A into B is equal to B into A. It is a commutative process. So, since that order does not matter, so these quantities are also symmetric quantities. Now, let us look at some of the important properties of these moments of inertia and product of inertia terms. Well, first of all, the moments of inertia terms Ixx, Iyy, Izz, since they involve sum of these squared quantities x square plus y square plus z square, etc. And square, when a quantity is squared, it is always positive, and two positive quantities summed will always be positive. So, it means that Ixx, Iyy, Izz, they will be always positive quantities. They will be 0 only when the body reduces or degenerates to a point. In that case, the volume integral will be 0, otherwise it will be a non-zero quantity. So, safely you can say that if the body is a finite body, it is not a zero volume body, then these moments of inertia terms will be always positive quantities. If the, now second point, if the body is thin plate like, if the body is in the form of a plate of uniform thickness, and also let us say the body is having uniform density, it is a homogeneous body, so that T and rho are independent of x, y, z. So, rho into T factor can be taken outside. So, I can easily see, and let us say thickness is along z axis, then the volume integral will be converted into area integral by taking T and rho outside, and also since the body is thin, the z coordinates of any point of the body will be much smaller than the y coordinate, and z square will be even further tinier or smaller than the y square quantity. So, approximately or up to second orders of infinitesimals, we can say that Ixx is equal to rho t taken outside into area integral, which is nothing but Ixx area. This is Ixx mass moment of inertia. So, to be specific, I should write m in the at the bottom. So, Ixxm, which means mass moment of inertia about x axis, is equal to rho t times area second moment about x axis, second moment of the area about x axis. Similarly, we can say about y axis and so on. Okay. The factor rho t, it is the mass density into thickness. So, it will be the density of material, but now expressed in terms of mass per unit area of the plate, because thickness has been already taken into account. So, it is rho t is the kilogram per meter square, that is mass per unit area. So, we conclude that the mass moment of area of a thin uniform plate equals to the corresponding second moment of area. Similarly, we can say for the product of area, that is the product of inertia for a thin homogeneous plate has a correspondence with the product of area of the corresponding figure. Okay. Now, if a thin plate has uniform thickness and homogeneous, consists of homogeneous material, then we will take the xy plane as the mid plane of the plate. Okay. so that the top surface and the bottom surface of the plate are symmetric about the mid plane, because thickness is uniform and whatever lies above same lies below the middle plane. So, then it is easily seen that Ixz and Iyz, because the area moments of will be the mass moments of area will be 0. The mass products of all inertia terms can be arranged in the following matrix form: Ixx, Iyy, Izz. These are the 3 mass moments of inertia, or simply moments of inertia, and these are the diagonal terms. And the off diagonal terms, we have already seen that they are symmetric. Ixy is equal to Iyx, Izx is equal to Xz, etc., etc. And these are the product of inertia terms. So, although it is a 3 by 3 matrix, it should have 9 terms, but there are effectively 6 terms, 3 diagonals and 3 off diagonals, because other off diagonals are symmetrically placed. So, again, if the given body has a plane of symmetry, let us say YZ plane is a plane of symmetry, then from the definition of the product of inertia terms, if I go back quickly to that definition, if there is a element at a particular distance from that plane, so there will be, because of symmetry, there will be corresponding element on the mirror image location. Then the contribution of these two symmetric elements will cancel out, because one is at a positive distance from the middle plane and the other is at a negative distance. So, whenever there is an axis of symmetry, you can be sure that the two products of inertia terms will be 0 because of that symmetry. That is, if Yz is a plane of symmetry, then Ixy and Ixz will be 0. Okay. So, this can be easily verified, since for any small element at a distance x from y, there is a similar element at a distance minus x from the same plane. Looking at the definition of the moments, now again, since Ixx, Iyy, that is mass moment of inertia terms, they have x square, y square, z square terms. So, if the body is spread out, that is during volume integrals you have elements which are at a larger distance x, y, z from the given axis, then their contribution will be more. So, if the body is spread out, then the moments of inertia terms will be larger. Now, we can also have polar moment, mass moment of inertia. Well, I am not carrying the term mass again and again, it is understood, because we are talking about mass moment of inertia. That is, suppose I want to find out Izz, that will be I rho times x square plus y square volume integral, and x square plus y square will be the radial distance of the element from the z axis. R is equal to x square plus y square. Okay. So, what does this mean? It is also, you can label it as the polar moment of inertia about z axis. Similarly, Ixx can be written as y square plus, so it will be the polar moment of inertia about x axis. Okay. And so, in this manner we can use the concept of polar moment of inertia. And if I sum up all the three mass moments of inertia, that is Ixx plus Iyy plus Izz, then using their corresponding expressions and adding them up, we will have twice the volume integral of rho times x square plus y square plus z square. What is this? X square plus y square plus z square. This is the radial distance of the particle from the origin of the coordinate system. So, it will be r vector absolute value square. Okay. So, r vector is the radial distance. Now, this quantity is it's a magnitude of a vector quantity. For every particle of the body, it is independent whether I take the x, y, z like this or this or this, if the origin is not changed. So, for the same origin, this quantity r vector absolute value of r vector is independent of the choice of coordinate system. So, it means that the sum of the three mass moments of inertia is invariant quantity. It is same in all the coordinate system. This property is very useful in solid mechanics. Now, let us introduce radii of gyration of inertia of a body. Just like we had radii of gyration of area of a given area. So, we will have corresponding quantities for the three-dimensional body. We will define kx, that is x radius of gyration, as Ixx divided by the total mass of the body, take a square root, Ixx over m square root. Similarly, ky, Iyy over m square root, etc., etc. Or alternately, Ixx is equal to mass of the body times kx square, Iyy is equal to mass times ky square, and Izz mass times kz square. So, what is the physical interpretation of these radii of gyration? You can treat them as the three coordinates of a point where the entire mass of the body can be assumed to be concentrated. So, let us say you shrink the given body continuously till it reduces to a total mass at a point. Okay, it keeps on shrinking, and mass, by conservation of mass, the total mass is not being reduced, but the density is being made higher and higher. Then we can say that the entire mass is located at a point, and what is that point? Its coordinates will be kx, ky, kz. This is from the point of view of the moment of calculation of the moment of inertia. Okay. For the calculation of the first moments of mass, you will have the center of mass or centroid, but for this moment of inertia, you have radii of gyration. Let us try to take up some simple examples to see how we can calculate the mass moment of inertia or various terms. Let me start with a simple one-dimensional example. That is, I am treating the body to be one-dimensional. There is only one variable, x variable, although there is a area of cross section and mass, etc. We will say that this area of cross section is very small as compared to the length, that is, the lateral dimensions are small as compared to the length, and effectively the cross section is uniform, the density is uniform, so that rho can be at most a function of x. So, a 5 meter long rod is shown. The density of the material is varying linearly along the rod length. So, it is no longer a uniform density, it is a variable density. Its density is 0.6 kilogram per meter at x is equal to 0, that is at the and it is 1.0 kilogram at x is equal to 5. I think I may need a correction, yeah. Instead of, let us say, because this point A is at minus 0.25 meter. So, instead of x is equal to 0, I will have minus 2.5 meters, and this will be plus 2.5, x is equal to plus 2.5. So, at A the density is 0.6 kilogram per meter, and B the density is 1.5 kilogram 1.0 kilogram per meter at 2.5. Okay, sorry for the error. Let us see, this density rho as a function of x is, because it is a linearly varying density. So, the simple equation A plus bx. So, rho as a function of x is A plus bx at point A, which is corresponding to x is equal to minus 2.5 meters. So, rho is 0.6. So, if I substitute x as minus 2.5, so A minus 2.5 b is equal to 0.6. At the right hand end, that is at point B, where x is equal to 2.5 meter. So, rho is equal to 1 kilogram per meter. So, 1.0 is equal to A plus 2.5 b. Okay. So, from these two equations I can solve for two unknowns. A will come out to be 0.8 and B will come out to be 0.08. Hence, the density rho is equal to 0.8 plus 0.08 x. So, we have determined the function which describes the variable density of the material, of the rod. Then Iyy is to be obtained. So, this is y axis at the middle. Okay. So, we have to find out the distance of any element of the rod from the y axis. So, that is the distance x, x square times rho x dx from minus 2.5 to plus 2.5, and this is a very simple integration, since rho is a function of x as we have determined. So, x square into 0.8 plus 0.08 x integrated along x from minus 2.5 to plus 2.5. Integration is very simple, and substituting the upper limit and lower limit, we find that Iyy is equal to 9.896 kilogram meter square. Okay. So, this is a simple one dimensional case, but here the density was variable density. Let us take up another example. Here we are asked to find out Izz and Ixx for a right circular cylinder of mass m. So, you can see that these axes are at the end. Z axis is along the length of the cylinder. The length of the cylinder is L, okay, from end to end, and the radius is R. So, the diameter is 2r along x axis, and the third axis is the y axis. Again, we can consider a small element which I have shown on a larger scale. This small element of the body, which is subtending an angle of delta theta. It is a narrow element, and the radial distance is dr, and the distance along the z axis, axial distance is dz. So, let us consider this problem. The arc length of that sector like body is r d theta. Radial distance I have shown, already told, is dr, and the axial distance is dz. So, the volume of this element is r d theta dr dz. This is a typical infinitesimal element in cylindrical polar coordinates. So, you must have learnt it in coordinate geometry or advanced calculus. So, Izz from the axis is the radial distance r square times rho into the volume element, that is r d theta dr dz, and the integration is from 0 to 2 pi along theta, 0 to r capital R along the radial direction, and 0 to L along the axial direction. Well, this integration is very simple. First of all, r cubed integrated from 0 to r will give me r4 by 4, and theta d theta integrated from 0 to pi will give me 2 pi, and dz will give me integration to simply L. So, you will have r square by 4 into rho into 2 pi into L. Now, what is the mass of the cylinder? Area of cross section is pi r square. So, into L will be the length, where L is the length. So, that will give me the volume times density. So, if you simplify this, it will be the total mass m times r square by 2. So, mr square by 2, that is the moment of inertia of a right circular cylinder about its axial direction, the axis z. Ixx, that is, you can recall x was along the diametral direction. So, about any diameter, if you want to find the moment of inertia, then y square plus z square into rho times dv, r d theta dr dz. So, again you can see that y square, once again if I go back to the figure, if I have to find out, this is the radial direction r. So, the y distance will be r cosine theta, because this angle is angle theta. So, r cosine theta will be replacing y, plus z square as such times the mass of the elementary body. So, if you simplify and carry out the integration, you will have two terms, first the r cosine square theta term and the second z square term. So, these are the two terms, and now I have to integrate them. You will find that the first term will give me rho times r4 by 4 pi L, plus the second term will give me rho times r square by 2 into 2 pi into L cubed by 3. Okay? That is the z square term integrated. So, if I again collect these terms, take out the common thing out, pi r square into L into rho. Pi r square is the area of cross section times length, that will give me the volume times density. So, the total mass times r square by 4 plus L square by 3. So, we have seen Izz, Ixx, and Iyy will be equal to Ixx, because the body is symmetric about any diameter, whether x diameter or y diameter, it will not be different. So, Ixx and Iyy are 0, and the product of inertia terms Ixy, Iyz, Izx will be also 0, because of the fact that the body is symmetric about, let us say, the middle plane. If I consider a plane over here, so that is the plane zy plane, the body is symmetric in the zy plane, body is symmetric in the xy plane, body is symmetric in the xz plane. So, all the three orthogonal planes are planes of symmetry. So, it means that the product of inertia terms will be also 0. So, if I write the inertia matrix for this body, right circular cylinder, then the terms are Ij. So, I going from 1 2 3, j going from 1 2 3. So, I11, that is Ixx will be m r square by 4 plus L square. Similarly, Iyy same quantity, but Izz is equal to m r square by 2. Okay. So, this is the final expression for the matrix of inertia, and the product of inertia terms are, as I have seen, they are 0. So, there are only 3 diagonal terms, off diagonal terms are vanishing. So, I think we can close today's lecture over here. So, we have learnt in this lecture the moments of inertia, products of inertia, and what is their correlation with the second moment of area and product of area, which we have learnt in previous lecture. So, their correlation for a thin uniform body, homogeneous body is very simple, that is rho times thickness, which is the area which is the density of the material per unit area. So, the correlation lies through that. So, the second moment of area about x axis is equal to the mass moment of area about x axis divided by rho t, or vice versa, this mass moment of area about x axis is equal to rho t times the corresponding area moment of area. Similar thing can be said about the products of area and versus the product of inertia. So, in next lecture we will be again looking at the parallel axis theorem and the rotation theorem for the mass moments of inertia and product of inertia. Thank you very much for your attention.